Welcome back to the ChemDoctor, and this is going to be the third video in the series on chemical kinetics. And I want to achieve two goals here. Number one, I want to take the viewer through practicing how to calculate an average rate, and then I want to introduce the concept of what's called a rate law, which has to do with how the rate changes in proportion to when we change the concentration of a reactant or a product. All right, so what I'm going to do is calculate the average rate of disappearance of NOI, and I will show you, like in the last video, how to find the rate of the other components that are in the reaction. So the formation of the NO, the average rate of formation of the NO, and the average rate of formation of the I. Then what I'm going to do is just go ahead and fill in the table. And what the viewer should do at that point, if you're still struggling with calculating average rates, is pause the video and go ahead and make the calculations for those rates and make sure that you can do it too before going on with it. So what we're going to do first is calculate the average rate of disappearance of the NOI for the time interval between 0 and 2 seconds. All right, and so and I'll come over here to do on the right side to do the calculation. So we set this up first. We're going to have a negative sign and then a delta sign for the change in concentration of the NOI, okay, as a function of the time. And I'll go ahead and put the interval in that we're working on. It's going to be from 0 to 2 seconds. And then this is going to equal, now remember what we're finding here is the slope of a line. So if I went up here and just freehand a quick graph, all right, where we have time on the horizontal axis, we have concentration of NOI. Here on the vertical axis, we would be looking at a curvature that would have this appearance. And we're starting with a concentration here that's 0.1. So you would expect the concentration of NOI to decrease with time. And again, the curve is going to flip over and become asymptotic to some final value, which is going to be determined by an equilibrium position. And right now we're finding for the time interval that's going to be the slope of the line very close to where t is 0. So if I was to mark 2 points on here and we would have a tangent, for example, along this line here, then we're finding the slope of the line pretty close to t equals 0. All right, and the 2 points are going to be 0 and 0.1 and 2 and 0.071. So remember, the slope is y2 minus y1, so we're going to have 0.071 minus 0.1, and this will be divided by 2 minus 0. All right, and we're going to use the negative sign to indicate that the concentration is going down, and it will be 0.145, and the units will be molarity per second. So the rate of disappearance for this time interval is, and I'll go ahead and write it in, is going to be minus 0.00145, and the units are molarity per second. I'll just put that up here. Okay, now I'll label this is the NOI, so it's very clear. And what we're going to find now is going to be the NO and the I. So the way that we do that for this time interval is we use the stoichiometry from the balanced equation, and we see that the rate of disappearance of NO is going to be equal to the appearance of the NO. Okay, maybe I misstated that, so I'll say it over again. The rate of disappearance of NOI will be equal to the rate of appearance for the NO, because they both have the same stoichiometry. For every 2 moles of NOI that go away, 2 moles of NO will be formed. And in the case of the I, only 1 mole of I will be formed. So the kind of curve you would expect for the NO would be a direct reflection of the curve that we have for the NOI, and the I is going to be, we're going to be splitting the difference. It's going to be, proportionately half of what you see for the NO. All right, now, so to find those rates then, we'll take, and I'm going to use labels here. I'm going to drop my negative sign now because we're finding the rates for the products which are being formed. And so we're going to have, here's our rate that we found for the NOI, and I'm going to go ahead and put a label on this. We're going to treat this as if it was like a theoretical yield problem or a limiting reactant problem. So we're going to multiply this by the ratio from the balanced equation. First we'll find for the NO, so it's going to be 2 NOs that are produced for every 2 NOI. And 2 over 2 is 1. So you see the rate of formation for the NO is going to be exactly equal to the rate of disappearance for the NOI. And I'll go ahead and insert that value here as a positive sign because its product is being formed. Similarly, I set up the similar kind of equation to find the I. All right, and I'll put my label in again because we're starting with, this is our reference rate, right? This is what we were given the data for, is the NOI. And now I'm going to solve for the I. And we have 1 I for every 2 NOIs. So the rate of formation of the I is going to be 1/2 the rate of disappearance of the NOI. All right, now we'll go ahead and insert that rate up here for the I. There. And all of these are in molarity per second. Now, I'm going to go ahead and fill in my table for the rest of these so we can get on to the next part of this presentation. All right, and one thing is, as you look at the data for the NOI, you can clearly see that its rate is decreasing over time, and that, again, that's what you expect because this is a reactant that is going away. All right, and let's see, my last rate value here is going to be 0025, and then as a reflection of this, right, these values will be the same in magnitude for the NO. All right, no negative sign because they're being produced. And then your I values are all going to be half these values in each case because of the stoichiometry of the reaction. All right, let's just finish this up. All right, so that's what your data table should look like. The average rates of these other things determined because we have a reference, and that reference is that we knew the time versus concentration data for the NOI. Now, what I want to introduce in the next part of this is I want to talk about the whole point behind the kinetics thing, and that point is to try and understand exactly how the reaction is happening, because the mechanism, how the NOI particles collide, the transformation they undergo during the collision, the energy it takes to do that is what controls the time of the reaction. So we have collisions going on between the particles. The particles have to collide in a certain kind of orientation, and each collision has to have a certain amount of energy in order for the reaction to happen. And this means that when we look at the rate of a reaction and we ask how is the rate affected in a proportional manner by the concentration of the reactant, what kind of relationship does this have? All right, now in order to figure this out, we are going to utilize an expression which is called a rate law. All right, so let's start with what we already know. So we can write how the concentration of the NOI varies with time, like we've already learned. So change in NOI over delta T, and this is equal to the rate and average rate of the reaction. When we push this analysis back as close as we can to T equals 0, we call this initial time kinetics. All right, and what we're doing there is we're taking this tangent as close as we can get to T equals 0, and the key reason there is because we want no reverse reaction happening. So we're only studying the relationship of the concentration, how the concentration of NOI is changing as a function of time, and how it's changing as a function of its rate. So we're going to set this equal to another type of expression. All right, and it is going to be a product of what we call a rate constant times the concentration of the NOI raised to an x power. Now, we had expressions for equilibrium, so it shouldn't be shocking that we're going to have now an expression for kinetics. The one thing that you've got to be careful about is this exponent that I just put up here. This can only be determined by the rate or by carrying out an experiment. All right, you cannot guess what this x value is, and you cannot determine it by the stoichiometry of the reaction. So we're going to call this value a special name. It's called the order of reaction, or reaction order, and I'll come back and talk more about that later. And then we have this rate constant here, and I'm using the word constant. That means that this value will be constant for any given chemical reaction that is carried out under, a certain prescribed set of conditions and at a certain temperature. This rate constant has wrapped into it the issue of collision frequency, the orientation, how the two particles collide, and the energy associated with initiation of the reaction. This I will also address later. The main thing right now to get from this is that this is what we're going to call a rate law. And the rate law really has, in reality, it has two parts to it. It has the section that deals with how the rate is related to concentration, and that part I will underline in blue. Okay, this is what we call the differential rate law. The differential rate law, and it relates how the rate changes with changes in concentration. All right, and then we have the part of the rate law that deals with how concentration changes with time, and that's this part right here that I'm bracketing in red. All right, so and it is related to the concepts that we've already addressed here, where we have the concentration of a reactant that's changing with time. Now, what I want to draw your attention to is the graph that I've done below, and what this represents is, what I did was I took the data set that we have here and I plotted the rate of the reaction. So that would be the rate of disappearance of NOI, but as a positive rate, as a rate of change without the negative sign. So what I did was I took this column of data, the rate of change of NOI, and I plotted it as a function of concentration. So the concentration of NOI at these different rates, all right, is shown on the graph below. All right, so on the x-axis we have the concentration of NOI, and on the vertical axis I have the rates. And what you're going to notice, what I've done is, through the middle of this graph, I've drawn what the linear correlation would look like if this data had a linear relationship between how the concentration was changing with its rate. And what you can see is we get a curved line out of this. The main point is that there is not a straightforward relationship in this particular chemical reaction between the rate of the reaction and the concentration of NOI. In other words, it's not a linear relationship. And this has implications for the determination of what we call the order of reaction. And that's what this is what we're going to learn about next in the fourth video. And with that, I'm going to go ahead and close.